So what we are going to do here is we are going to prove that the supremum of the sum is less or equal that the sum of the supremums. We have f plus g bounded functions. So the completeness property of the real number says that that there is a supremum in R for any non-empty set S of the real numbers that is bounded from above. Okay, so we are going to introduce some notation so that it's easier for us. So we have that the supremum of the sums of f and g is going to be a, the supremum of the set of the f of x is going to be b, and the supremum of the g of x is going to be c. So what we are going to do is the following. So if we have f of x plus g of x, this is going to be less or equal than a, which is the supremum of the sum of f and g. F of x is going to be less or equal than b, which is the supremum of the f of x, and g of x is going to be less or equal than c, that is the supremum of the g's. Now we are going to call these 1, 2, 3. So if we add 2 and 3, we get the following. So we get f of x plus g of x. This is less or equal than b plus c. But this is equal to the supremum of the f of x plus the supremum of the g of x. Now, we also have the following, okay? This expression here is going to be an open bound for the following set. So if we have f of x plus g of x such that x belongs in D, this set over here, b plus c, is an upper bound for this. Okay, so what we have is that this is less or equal than the supremum of f of x plus the supremum of g of x. But the supremum of this, so we have that f of x plus g of x such that x belongs in D is bounded by the supremum of f of x plus g of x. Since this is the supremum and this is just an upper bound, that means that the supremum has to be less than the supremum of f of x plus the supremum of g of x. And that's exactly what we wanted to prove. A similar property holds for the infimum.